Finally, buffer solutions. What are buffer solutions? Buffer solutions are solutions which resist large changes in pH when either acids or bases are added. And buffer solutions are found especially in biochemical fluids. For example, blood. You may recall that the pH of blood is around 7.4, and I mentioned previously how if it deviates from it even slightly, your body is not going to be comfortable with it. You might be hyperventilating, and then there might be other more complicated situations that might arise. And even if it deviates from 7.4 to 7 or 7.1, you might need hospitalization, to say the least. So blood has to make sure that the pH remains close to 7.4, otherwise it's not good for the body for various reasons. So how does that happen? That happens using a natural buffer solution that makes sure that the pH does not change. Now, whenever you add an acid to liquid water, for example, the pH will drop precipitously. If neutral pH water you have, just neutral water, DI water, the pH is 7. Adding just 10 ml of HCl to that might drop the pH a lot depending on the concentration of the HCl. Similarly, if we add a very little NaOH, the pH will go up very quickly. So if that is going to be the condition by how the pH changes, how can a solution make sure the pH does not change that quickly? For example, if you go and eat some acidic fruits, you may assume that if your body does not have a buffer system, then the blood pH will drop quickly as the acids from the fruit enter your blood. On the other hand, if you eat something that's basic, then your blood pH may go up very quickly as well. How exactly is the blood pH maintained around 7.4? Using buffer solutions. Buffer is a very common word. We use that in different fields as well. For example, if there is a storm coming and if there is a likelihood of some river breaking through its boundaries, there might be a buffer wall that might be put around it that may prevent it from spilling over. Okay. Also in military, there might be buffer zones where there is no war taking place. So similarly, a buffer solution is used to prevent something from spilling over. In this case, a change in pH. Now here is a buffer solution example where a buffer can exist of a weak acid and its conjugate base or its salt, or a weak base and its salt, a conjugate acid. We will look at the first example, and the logic, whatever it is in there, applies to the other weak base and its conjugate acid example as well. So here is an acid, acetic acid, a weak acid. When you dissolve it in water, it establishes an equilibrium, creating its conjugate base, and here is the other part of the equilibrium. So here is the acid and its conjugate base. You can either create this by just adding acetic acid to water and allowing the equilibrium to establish, or you can control how much CH3COO minus you have if you add sodium acetate, for example, a salt which will completely ionize. Being a salt, it is completely it's a strong electrolyte, so completely ionized, giving you acetate ions. So thereby you know how much acetate ions you have in the solution and how much acetic acid you have. Now you have a buffer solution. That is all a buffer solution is. To this solution, if we add some HCl, the pH will not change as much as if we had added HCl to just pure liquid water. Similarly, to this solution, if we add NaOH, the pH will not increase as much as it would have increased if we had added NaOH just to pure liquid water. That happens due to the Le Chatelier's principle, and as we will see now, how does that work? If you were to add a stress to this equilibrium, as we learned from Le Chatelier's principle, what happens? The stress being the addition of, let's say, H3O plus. If I come along and add HCl, HCl being a strong electrolyte will dissociate to give me H plus and Cl minus. Cl minus is not part of this equilibrium, so it doesn't have any effect on it. But H plus or also the same as H3O plus, because H plus exists as H3O plus in solution as I told you previously. So we are adding H3O plus when we add HCl. And as you see, there was already acetic acid acetate buffer or acetic acid acetate equilibrium established in the solution. When we added HCl, we basically added more H3O plus. So if H3O plus that we just added was going to lower the pH, that's not going to happen immediately. Instead, it's going to affect this equilibrium. We have just added a stressor to this equilibrium by adding H3O plus. Hence, the equilibrium will shift to the left. Because we added this, it must be consumed, shifting the equilibrium to the left. As it shifts to the left, the added H3O plus, most of it that was added will be consumed. Since most of it will be consumed, the pH, which depends on the concentration of H3O plus, will not change a lot. pH may change slightly, but not a lot. It all depends on how much HCl we are adding. By the way, in the end, there is such a thing called buffer capacity, which you will see soon as well. But adding a little bit of HCl may not overload the buffer, and there might be enough CH3COO minus to react with the added HCl and added H3O plus through HCl and shift the equilibrium to the left, thereby keeping the pH the same. If you were to add OH minus, how would that not change the pH in this case? If you added OH minus, it would react with H3O plus as it says here, and if it reacts with it, it forms liquid water, because OH minus and H3O plus form liquid water. So that would consume our H3O plus instead of adding it. Now that we are adding stress by removing H3O plus, then the equilibrium shifts to the right as acetic acid and water react to form CH3CO minus and H3O plus. So the H3O plus, which was just removed by adding OH minus and trying to increase the pH, well, that doesn't happen because the equilibrium shifts to the right and more H3O plus is created that will keep the pH at the level that it was. So this is how a buffer works. Okay, whether we add H3O plus or whether we add OH minus, the equilibrium will shift accordingly. If we add H3O plus, the equilibrium shifts to the left, consuming the added H3O plus. If we add OH minus, the equilibrium shifts to the right, creating more H3O plus. Okay. So here is what happens, color coded. Add OH minus, equilibrium shifts to the right because we are consuming H3O plus, equilibrium shifts to the right. And if we add H3O plus, equilibrium will shift to the left. So as I was saying, there is something called buffer capacity. We cannot just endlessly keep on adding HCl or NaOH and expect the pH not to drop or not to increase forever, because we only have limited amount of CH3COO minus and CH3COO minus, I mean CH3COOH and CH3COO minus, to actually compensate for any sudden added H3O plus or OH minus. If we add too much of H3O plus, for example, we may add way more H3O plus than we have CH3COO minus to react with it and move to the left. In that case, we have our buffer capacity that is just not able to meet the added change in pH that is being attempted. Think of also if there is a storm coming and there is at the river bank, if there is a buffer wall that's 20 feet high, but if the water in the river rises greater than 20 feet, then water will spill over and it will go beyond the buffer. Similarly, it can happen here as well. So the concentration of CH3CO minus and CH3COO minus, I mean the concentration of this acid and its conjugate base are important whenever we design a buffer. Okay. So here is how a buffer solution is made, and we can find out the Ka of this equilibrium. As we know, Ka of it involves the H3O plus concentration times the conjugate base concentration over the acid concentration. And if we want to know the pH of the solution, we can actually find the pH as well by uh, rearranging this equation for Ka. So here is the Ka value for acetic acid, for example, being 1.75 times 10 to the negative 5 molar. Sorry, not molar, it's a Ka is a unitless term. So that's your Ka value. And if we rearrange this equation to have H3O plus on the one side, we have this form given on the bottom. H3O plus concentration equals Ka times the acid concentration over the base concentration. Now in this problem, both the acetic acid and sodium acetate concentrations are the same. Okay, so if their concentrations are the same, that means the CH3COOH is 2.0 times 10 to the negative 2 molar, and sodium acetate, which will completely dissociate to give you sodium ions and acetate ions given here, tells us that the acetate ion concentration is also the same, 2.0 times 10 to the negative 2 molar. Then we plug in all those values and we can find out the H3O plus concentration. Again, in a buffer condition, the acid concentration, H3O plus concentration, the pH that we want to know, we can find out first by finding the H3O plus concentration equals the Ka times the acid over conjugate base. Whether it's a different acid and a different base, it does not matter, as long as we know the concentration of the acid and its conjugate base and the Ka value, we can find out the H3O plus concentration, and then we can take the negative log of that to find the pH. So here the negative log of the H3O plus concentration gives you a pH of 4.76. Right, so that allows us to actually use a version of the rearranged form of the equilibrium expression we saw, and we are going to look at it in more detail in the next video.